Here we're going to show how you can use vectors and vector arithmetic to prove some claims in geometry. So first we're going to ask, let M1 and M2 be the midpoints of AB and AC in some sort of triangle. We're going to show that M1, M2, the line between M1 and M2, is half the length and parallel to BC. So the first thing we're going to want to do is turn everything into vectors. And then, once we've done that, we're going to try to see what kind of question are we trying to answer in vectors. So let's go ahead and just put lots of arrows in lots of places. And we'll have BC, I guess, going this way. And we'll have M1, M2 going in the same direction. So what we're asking, we're trying to compare the vectors BC and M1, M2. One thing we want is that we want them to be parallel. Parallel just means that BC times some scalar multiple gives me M1, M2. Because remember, multiplying by a scalar multiple doesn't change the direction, it just changes the magnitude. So if we can get 1 just by multiplying by a scalar multiple, then it means they're parallel. And if it's half the length, well, that means that the norm of BC, 1/2 the norm of BC equals M1, the norm of M1, M2. We also know that if you take a vector and multiply it by a scalar multiple, that just scales up the length. So we notice that we can actually wrap up both of these, are just saying that M1, M2 is going to equal either plus or minus 1/2 of BC. Since it's multiplying by a scalar multiple, that tells us it's pointing in the same direction. And since that scalar multiple is 1/2, it's telling us that we've modified the magnitude by 1/2. The plus or minus just says that maybe they point in opposite directions, but they're still parallel. We drew it so that they're pointing in the same direction, so all is good there. So let's see if we can go ahead and prove that. Well, what is AB? AB, if you look at our picture, since this is the midpoint, M1 is the midpoint, that's going to equal AM1 plus M1B. And what's AC? Well, that's just going to equal AM2 plus M2C. And one thing we notice is that for each of these, AM1, M1B, and AM2, M2C, those are all actually the same thing. Well, okay, they're not all the same thing, but AM1 is the same as M1B because they're both the same length because M1's a midpoint and they point in the same direction. And similarly, AM2 and M2C, both the same length, both point in the same direction. So we can actually rewrite this as 2AM1. We could have also done 2M1B, but my gut just tells me that this is what I'm going to want. So this also we can write as 2AM2. Okay, how does that help me? Well, I know that BC is going to be given by the vector AC minus the vector AB. Because we subtract the endpoint from the beginning point, which is going to end up being 2AM1, sorry, It's going to be 2am2 minus 2am1. And what's 2am2 minus 2am1? Well, that is exactly the vector 2 m1, m2, just looking back at our picture. Because m1, the vector from m1 to m2 can be found by taking the vector from am2 and subtracting the vector from am1. This is why it's important to kind of have those subtraction ideas in our brains. You know, this general picture that if we have a vector A here and a vector B here, then the vector pointing from A to B is going to be the vector B minus A. And that's just the idea that we use all over the place here. So, what do we have here? We have that BC equals 2m1, m2, and all we needed to do is divide each side by 2, and we get exactly what we want. 1/2 BC equals m1, m2. And that is exactly what we were trying to prove, and we're all done. So we didn't have to look at angles, similar triangles, anything like that. We were just able to prove this directly using vectors. So that's kind of fun. Okay, let's go ahead and look at this here. So we're going to prove that every inscribed angle of a semicircle is a right angle. First of all, what do we mean by an inscribed angle? That just means if you take a semicircle, kind of points opposite, and then you pick any point on the circle and draw lines between the point on the edges of that semicircle and the point you chose on the circle, that angle will be a right angle. It's just this picture. So since we have circles, we know a lot of lengths are going to be the same. So let's draw some vectors here. Here's a vector. We'll call this vector here A. And I could call this vector here B, but, you know, I can call it something better. Because since this is a circle, the radii all have the same length, and this just points in the opposite direction. So I can just call this negative A. We have another vector here. This is another radius vector. We'll call this B. And now I'm interested in two vectors. We'll draw some arrows. This vector here will be negative A minus B. Remember, B is pointing this direction. And this vector here well, that's going to be A minus B. And what are we trying to do? We're trying to tell, are these orthogonal? The good news is we have an easy way to do that. We just take the dot product. So we'll take negative A minus B and dot it with A minus B and see what we get. Well, this is going to be negative A dot A plus A dot B minus B dot A plus B dot B. So these are gonna cancel, and I'm gonna rewrite this. We know that A dot A is just the norm of A squared. So we're gonna have the negative norm of A squared plus the norm of B squared. And we're interested in what this is. Well, since A and B are both radius vectors, they have the same length, so their lengths are the same. This means that when we subtract these, we're going to get 0, which then shows us that, yes, negative A minus B and A minus B are, in fact, orthogonal. So, there's a few examples of how you can use vector arguments to prove claims in geometry.